So let us come to a discussion and a summary of this course, which I do on slides. So we have studied in this course theoretical aspects of uncertainty quantification. And in addition to the modeling things that we have done, we have mainly looked at high-dimensional integration, and that was the why to do it like this part. The setting was that we have a true integral that we ultimately compute when we compute an expected value of a certain quantity of interest of a computational model. We assume it's expensive to evaluate this model and that we are in high dimensions. We approximate this by a quadrature rule which loses endpoints in total. And that could be Monte Carlo, that could be a tensorized grid, that could be a sparse grid. In the fair comparison, and a fair way of saying a method suffers from the curse of dimensionality if the cost, so the number of points necessary to achieve a certain accuracy, the epsilon cost increases in a bad way with D. And then we say in this lecture, in this class, that the method suffers from the curse of dimensionality. I want to point out again that in the literature, there is no definition. There's just a sloppy saying of doesn't suffer from the curse of dimensionality if the convergence rate is okay, which doesn't mean anything in practice. So going through the methods, we looked at the Monte Carlo method. The Monte Carlo method, interestingly, has an error inequality, which we interpreted also. If you set the experiment up properly, the method converges with the square root of n, which is robust but also slow. And there is a constant in this error estimate, which is the variance of the function, which should not behave in a bad way on the function on the dimension d, which, however, it sometimes does. So multi-level Monte Carlo is a smart variance reduction that also can be analyzed, should be analyzed, and it ultimately allows you, under some assumptions, to bury the additional cost due to the discretization in the Monte Carlo error. Then there was quasi-Monte Carlo, but I prefer the term number theoretic integration or quadrature methods because that's what they are. They rely on an error estimate that consists of the Hardy-Krause variation as the one term multiplied with the discrepancy. The discrepancy, recall, measures the homogeneity of a point sequence in a certain set. So I take a hyperrectangle that's centered at 0. Look how many points are in that hyperrectangle, compare that to the volume, and that's my discrepancy, which should ideally be 0 if the sequence is perfectly homogeneous, but it's points, so it can never be 0, but as small as possible. And then this is kind of the other term in the error estimate that we got by integration by parts is the Hardy-Krause variation, which demands something that I find is unusual in normal analysis, the existence of such a derivative, which is the dth partial derivative with respect to all of the different variables in there. Then there was quasi-Monte Carlo as an error estimate. Yeah, so Cox-Malawka inequality is error is bounded by Hardy-Krause variation times discrepancy. Minimal discrepancy sequences, now that is number theory really. That's the best you can do. They behave like this, log n to the d times n to the minus 1. If I look at n to the minus 1, which many people often do, I say, oh, convergence rate 1. But don't forget the log term. The truth is that you see the order 1 only if n depends exponentially on the dimension d, which you can ask yourself, does it beat the curse of dimensionality? No. Does it mitigate the curse of dimensionality like I've written here? Maybe. Then there's tensorized grids, and the problem with tensorized grids was that the error of the multidimensional rule is actually the one-dimensional error. And then if I measure in terms of the total number of points, I get a bad behavior in the dimension here. So I get an effective convergence rate, which is alpha over d, which in the literature now is called curse of dimensionality. But it's also the curse of it also suffers from the curse of dimensionality according to our sharper definition. Then there's stochastic Galerkin, which is not a quadrature rule. It's the only intrusive method that we considered. We make an ansatz for the solution. Yeah, it's an expansion in orthogonal polynomials. It's a so-called spectral method in numerics. And we assume that our data to solution map is given implicitly. So there's an equation which relates the input, C, the random variables, to the output, U of Z. And then I do an ansatz and a Galerkin projection, and then I get a system for the expansion coefficients, hopefully, and in most cases I do. And the error typically depends on the best approximation error. So how good is the space that I've actually chosen here? It's the linear space given by the polynomials. What was important in that game was total degree versus max degree. In higher dimensions, it's not clear what the degree of a polynomial is. So the total degree says if I write the polynomial as a multi-index, I'm counting, so I'm summing up over all the exponents. So for example, the polynomial x squared times y in 2D would have total degree 3 because 2 plus 1 is 3. And I can count how many terms I have. And then there's another notion, which is the maximum degree. It's just, well, the maximum that I have. So in that sense, the polynomial x squared times y would only have degree 2. And well, if I ask for the polynomials of total degree n or max degree n, then there is n plus d choose d of total degree and n to the d of max degree. So it's far more polynomials of max degree than of total degree. And by saying I want to integrate the total degree exactly, I'm winning over this one. Not exponentially, but good enough. And then we moved to sparse grids, and for sparse grids and for many other methods, I think that smoothness or the smoothness assumptions are important. So we looked at notions of smoothness, and one takeaway that cannot be stressed directly enough is that the notion of smoothness that you know from school, you know a function is differentiable and you know from your first semester, is actually not a good notion. What's much, much better for smoothness is a compression property. So if I expand a function in terms of orthogonal polynomials, say, so here's a Chebyshev expansion, if the coefficients decay fast enough, so here with order S, that is related to smoothness, to differentiability of order S. Yeah, in that sense, how fast expansion coefficients decay to 0, that's real smoothness, because the faster they do, the more of them I can throw away. Yeah, so I can compress the information that's inside the function. And we did something that I really, really like, Sturm-Liouville theory. So you have this for these orthogonal polynomials, this relation between, differentiability and order of convergence. And well, what also used this assumption is sparse grids. So when you looked at the error estimates and I do a multi-dimensional Chebyshev expansion, I needed to assume that the expansion coefficients decay faster than normal. So it decays in every one of these coefficients at order S. If I translate this now into the classical smoothness, it means that this partial derivative exists. So assuming S equal 1, we know that guy. We've seen this for quasi-Monte Carlo. It's the thing that's in the Hardy-Krause variation, which means, again, a weird partial derivative, actually. And then I get also something that's very similar to quasi-Monte Carlo, namely error estimate that has an n to the minus 1 term if S is equal to 1, polluted by a log n term, which again dominates everything if D is really, really large. So in order for this to dominate, for this one, for the convergence rate S, or for the convergence rate 1, I really need a lot of points, as before. There is an additional thing also, so like a common theme of all of this is that in order for this method, for a UQ method to really work, there is no magical method. There's not Monte Carlo or any of these other methods that are better in a way that you can tell from the error estimate directly And it's that, well, there is no method that's better for everything. Yeah. The take-home message is, if you think about the curse of dimensionality, if you put all of these error formulas together, the only way to fight the curse of dimensionality is to identify and exploit special structure of the model. That means I need to know the expected value that I compute. I need to understand the model. I need to understand the certain kinds of smoothness that there are. And those I need to use, those I need to identify, and then I need to choose the right method for this. Does this high order partial derivative exist? Yes or no? So that's the take home message. And let me mention one thing that I wanted to mention about the curse of dimensionality. One last thing. So if you look into this, the classical curse of dimensionality, which says, well, if my convergence rate behaves badly on the dimension D, that's the curse. And then one can say, well, I choose alpha equal to D, and then that's fine again. And then one says, well, sounds like a Münchhausen trick, right? I'm just solving the problem that I have here by assumption that alpha, the smoothness, scales with the dimension D. But you should be aware that that's precisely what sparse grids do. Yeah, so here, this assumption means a certain partial derivative exists and it's D. It's an order D partial derivative. So I'm actually assuming that the smoothness depends on dimension D. I'm doing this for sparse grids. I'm doing this for quasi-Monte Carlo. Yeah. So again, all of these methods, so there's no magic method. These methods are, however, interesting, well-designed methods that work even in a little bit of higher dimensions, but you need a lot of brain and a lot of trying out to see what the method of choice is in your application.